Here, we're going to talk about tilings. Now, a tiling, in its most basic sense, is just a way to cover a two-dimensional plane with shapes. And we're going to talk about certain kinds of tilings. But first, we'll start with definitions. A tiling is a covering of the infinite plane by non-overlapping regions called tiles. So when covering the plane, you need to put rectangles together somehow. You can't say if one rectangle is like this and then the other goes like this. You need them to be non-overlapping. And each piece we call a tile. Now, the tilings we'll look at first are edge-to-edge tilings. So a tiling is edge-to-edge if, kind of a long definition, if for each tile, each edge coincides with the entire edge of a bordering tile. Now that's, I think, a lot of words, but I think an example can illustrate an edge-to-edge tiling quite nicely. So here in this example, we're going to show two of them. So right here, I'm going to show the plane by just a large rectangle like that, and we're going to fill in the rectangle with tiles. And this first example is going to be edge-to-edge. The second one will not be edge-to-edge. So to fill it in with tiles, I mean, there are many ways you could do it. Just for this example, I'm just going to draw in some horizontal lines. And our tiles, we'll say, are these rectangles. So here we have 4 of those rectangles filling in the top. And again, we'll fill in with 4 more rectangles on the next row, 4 more rectangles on the next row, 4 more on the next row, and so on. And you can see, if you continue that pattern in all directions, the infinite plane will go on in all directions, of course. We can fill in that plane with rectangles. And we did it by dividing it into parallel strips and then filling them in with rectangles. Now notice, that first example right there is an edge-to-edge tiling. Now why is it an edge-to-edge tiling? Well, if you take any rectangle on this, one of the edges coincides identically with an edge on another. So that is edge-to-edge. You can check any of those tiles. Now one which is not edge-to-edge, I'll just construct like this. Let's say instead we're filling it in with squares. Let's pretend those are the same height. We're going to fill it in with only squares that are the same size down here. Well, right there we have some squares. But what if we're filling in all of the space? So what if on the next parallel strip, so you can fill these squares in infinitely on that side, infinitely on this side. What if on the next strip instead you've just shifted everything over a little bit and you filled it in with squares like this? And you kept going in the other direction too with squares, and everything kept going on. These should all really have like dots going in all directions. Writing all those dots is kind of annoying because they are infinite. And then on the bottom, we'll again fill in with squares just like this. Pretend they're squares. And so on. This tiling down here, well, it is a tiling because if you extend in all directions, it will cover the entire infinite plane. But it is not edge-to-edge tiling because if you look at this edge, right there, that doesn't coincide with the entire edge of a bordering tile. That corresponds to this piece of this edge and this piece of this edge. So an edge-to-edge tiling is one where the edges match up entirely. And the next definition, a regular tiling, is an edge-to-edge tiling which uses only one type of regular polygon. Now remember, a regular polygon is a polygon where all the sides are the same length and all the angles are the same. So a regular polygon, which is what we will look at first, is a tiling of the exact same shape where all edges meet identically with some other edge. And we can actually jump straight into a theorem, and we will actually prove this theorem. So theorem. So remember, a tiling fills in the infinite plane. A regular tiling fills in the infinite plane with the same exact shape, and all the edges match up nicely. So a question could be, well, we know all of the regular shapes. You know, there's the regular 3-gon equilateral triangle. The regular 4-gon is a square. The regular 5-gon, we can draw that, 6-gon, and so on. So the question could be, for which shapes does a regular tiling exist, or do irregular tiling exist? Well, there are 3. And we can prove that. So let's state this as a theorem and then prove it. The only regular tilings have triangles, squares, or hexagons. So this theorem says we can fill in the infinite plane with equilateral triangles, with no overlap and with no gaps between them. This theorem says we can do that with squares also. We actually saw down here, well, we didn't see exactly how you could use squares to do it, but you might have an idea how we can use squares to do it based on these 2 examples. We can do it with squares. We can also do it with hexagons. So this theorem says all of that. It also says we can't do it with pentagons. We can't do it with heptagons. We can't do it with octagons, nonagons, decagons, 11-gons, 12-gons, or anything else. And we will prove this. We will prove it right now. I just need to put the eraser down. I have a different eraser than my magic eraser. My eraser doesn't fit down there. So to prove this, let's make an observation. Actually, no, let's show how it works for triangles and squares first, then make an observation and show what happens with 5-gons or 6-gons. So, triangles. So, the triangles, remember, are going to be equilateral triangles. Well, let's draw a space. Let's draw a 2-dimensional space. Let's break our 2-dimensional space into a series of parallel horizontal lines. So we have a 2-dimensional space. We're going to split it into strips. And now let's just fill it in with triangles. They all have to be the same triangles, and edges have to match up. Well, here's one. How can we fill it in after this? Well, right there, that's the same equilateral triangle. That's the same equilateral. Why are these all the same equilateral triangle? Well, we can do this. Keep going over like this, and so on. We can do this. What are the angles in an equilateral triangle? Well, you might remember from a geometry class, the angles in an equilateral triangle are all 60 degrees. The angle on a straight line is 180 degrees. So all of these add up to 180 degrees. So we can fit them on this line with no gaps. And we can keep going like that. Well, that's great. On that one strip, we filled it in with triangles. But what about the next strip? Well, we filled it in with triangles in an edge-to-edge manner. What about the next strip? Well, we can do that down here too. But we need it to be edge-to-edge. So right here, we're going to take this edge, let that be an edge of our next triangle, and then just draw the triangle like that. And you can keep going in the same manner, filling it in with triangles. Now what about down here? What if we just did like this? Would that work? Well, sure, it would be a tiling. But would that be a regular tiling? Or sure, that would help create a tiling, I should say. But would it be a regular tiling? Well, I ran over from my eraser, walked over from my eraser, so you might suspect it is not. Now, why does this not work for a regular tiling? Well, this edge, the top edge of this triangle, does not coincide exactly with an edge before it. So we can't shift the triangles over like that. we need to preserve this same pattern by matching edges up like this, and so on. And I'm not going to draw the next row, you keep continuing. But right here we see a tiling. So this is a regular tiling with equilateral triangles. What about squares? Squares, looks like that. 90 degrees in all angles. Well, we already saw how we could make it not edge to edge down here by shifting the square over a little bit. But again, let's divide our two-dimensional space into strips. And it goes on in all directions, but we can just fill this in with squares like this. There's a square, 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 and so on. And down here we do the same thing. We can't shift it over. We need to preserve, well, we need the edges to coincide. Square, 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 and so on. Square, 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 and so on. And we get a tiling with squares. Tiling with squares looks like, what, a sheet of graph paper. What about fivegons? What happens with a fivegon? Pentagon. Well, and then we'll figure out what happens with hexagons. Actually, you might be able to see what happens with hexagons with this. There are hexagons in there, but we'll look at it a little differently in a moment. To figure out, so what about pentagons? Let's call them pentagons instead of fivegons. Pentagons. Question mark. A regular pentagon looks something like this. That's a terrible pentagon. Regular pentagon looks something like that. I should have written a sentence down here. This is a regular tiling with squares. This is a regular tiling with squares. Question mark down there, what am I thinking? With squares, period. What about pentagons? Well, you can try filling it in with pentagons and matching them up so the sides coincide. But let's first recall a result from geometry. Recall. We're actually going to recall two results. (180 degrees times n minus 2 gives us the total number of degrees inside an n-gon, any n-gon. The total number of degrees, so if you add this angle plus this angle plus this angle, any or all of the angles in a triangle add up to 180 times 1 degrees. All of the angles in a square add up to 180 times 4 minus 2. All of the angles in a square, or in a quadrilateral, add to 180 times 2, 360 degrees. So I'm going to recall two results. The interior angles in an n-gon add to 180 times n minus 2 degrees. So if you have a shape with 20 sides, the total number of degrees inside the shape are 180 times 18, which is whatever it is, 3240 or 2340 or 3240, I think, because 18 squared is 324. So there's our first recall. We're going to actually use that to recall another result, which my guess is everybody has seen that result. But if the total number of degrees in an n-gon is 180 times n minus 2, then we could say the interior angle in, maybe I'll say each interior angle. Each interior angle of a regular n-gon is what? Each interior angle of a regular n-gon. Well, the regular n-gon, all of the interior angles are the same. So if the total number of degrees in an n-gon is 180 times n minus 2, there are n angles, so the interior angle of each interior angle of a regular n-gon is the total number of degrees divided by the number of angles. And of course, the special case here gives us 60, because if n equals 3, is this many degrees, I should say, to finish that sentence. So if n equals 3, well then you get 180 times 1, which is 180, divided by 3, gives us 60 degrees at each angle of a triangle. How about a square? If n equals 4, 180 times 4 minus 2 divided by 4, well, 2 divided by 4 is a half, and 180 divided by 2 gives us 90. What about a pentagon? Because that's the one we're looking at. How many angles are on an interior angle, or how many angles? How many degrees is an interior angle of a pentagon? Well, let n equal 5. 180, 5 minus 2 is 3, divided by 5. You could do 180 times 3 first. I'm going to do 180 divided by 5 first. 180 divided by 5 is 36. How did I get 36? Well, 180, well, I didn't even think of 180. 18 times 2 is 36. So 180 times 2 is 360. 360 divided by 10 is 36. Because multiplying, or dividing by 5 is the same as multiplying by 2 and dividing by 10. So 180 divided by 5 is 36. 36 times 3 is 108. Yeah, that's a terrible 8. 36 times 3 is 108. So there is our first observation for this proof. Maybe I should have written proof. I don't think I've written proof yet in this class. Maybe I have, I don't know. Let's call it a proof, because it is a proof. So, first observation, Pentagon's angles are all 108. And now I'm going to erase this, because I might need this board. Next observation. What happens at a vertex in a tiling? Well, at a vertex in a tiling, you're going to have shapes coming out of it. At a vertex, you're going to have edges coming out of it. What do these angles, these 4 angles here, measure to, or add to? Well, they add to 360 degrees. And you can see that. Here we have 90 plus 90 plus 90 plus 90, 360. Here we have 60 times 6, 360. There are 360 degrees in a circle, by definition. So there is our next observation. At a vertex, they must add to 360 degrees. Well, let's try filling in space with pentagons. Here, we're not going to divide it into horizontal lines because, well, you can imagine if you tried to fit pentagons on a horizontal line, well, there's going to be a gap somehow. I can't draw 2 pentagons next to each other like that. Well, I can, but I'm not going to. You can't arrange them on a horizontal line. Try and see what happens. But let's just try filling in 2-dimensional space with a pentagon. I'm not going to put boundaries on the space because we don't need boundaries. So here's one pentagon. That's a pretty nice pentagon. So let's put another pentagon on this side. Let's see if I can draw a nice pentagon here. Not bad. Okay. What happens? Let's try to fill in this space up here. 108 and 108. we can figure out this angle. What is that angle? So that angle is 360 minus 216, because 108 plus 108 is 216. So that angle is 144, is that correct? Yes. So that angle is 144 degrees. Well, 144, well, that's good. We can fit another pentagon in there. Matching up the sides, of course. How are we going to fit a pentagon in there? If I were a better drawer, this would have been easier. Okay, pretend that's the same pentagon. So right here, we have 3 pentagons. And we can fit 3 pentagons like that, despite what the drawing may look like, because we have 308ths meeting at a point. What is this remaining angle? That remaining angle is 36 degrees. So you can see, if we try to fill it in with pentagons, at this point, we're going to have this wedge that we can't fill in. We can't fit another pentagon in there. So pentagons cannot tile, I should say regular pentagons, cannot tile, not tire, tile the plane. Because you could try fitting these pentagons together, you're going to have this wedge of uncovered territory. Because we can't just throw another pentagon on top of this, because that would create an overlap. There's a picture in the book with 3 pentagons like that in section 20.1 or 2, or 20.1 or 2. It's a little better than this drawing. But right here, we tried filling it in with pentagons, and just notice we used 3 pentagons and we reached the conclusion that we couldn't fill in this entire space. So what about hexagons? So hexagons. Well, let's draw a regular hexagon. So there's a regular hexagon. What's the interior angle of a hexagon? That's not a perfect regular hexagon. The interior angle, 180 times 6 minus 2 over 6. Well, 180 divided by 6 is 30. So 180 divided by 6 is 30. 6 minus 2 is 4. So each interior angle of a hexagon is 120. Well, that's great. So let's try filling in space with hexagons. And again, we have to match up edges. Well, okay, there's one. Let's work toward this direction. That's, I can draw it better than that. And hexagons are easier to draw than pentagons. I should be able to do that much better. A little better. Not a little better enough. There, okay. Those are the same hexagon. Well, what happens here? We have 120. We have 120. So what is this angle down here? Well, that angle is 360 minus 240. 240 because 120 plus 120 is 240. So this angle down here is 120. Well, that's perfect. We can fit another hexagon in there. And how about over here? Well, again, how many sides are a hexagon? 6. 1, 2, 3, 4. Let's see, that one's parallel up there. And then that should go down like that. Right here, we could fit another hexagon because we have 120, 120, and another 120. Up here, again, we can fill it in with a hexagon. And you can keep filling it in with hexagons because all of these gaps that it creates are going to have, the angles are going to be 120 degrees. So you can see that's a pentagon. Oh no, it's not. That's a hexagon. So you can see that it works with hexagons. Now, what about 7-gons and 8-gons? So this, so we showed this theorem for triangles. We showed it for squares. We showed that it doesn't hold for pentagons. We showed that it does hold for hexagons. What about larger than hexagons? Well, so let's say larger than 6-gons. Well, we'll go through an argument quite similar to the pentagon argument. Let's try a 7-gon. What's the interior angle of a 7-gon? Well, it's 180 times 7 minus 2 all over 7. What's that number? 180 times 5/7, that's, I don't know, it's 130-ish, let's say. It's somewhere around 130. So let's see what happens if we push up angles of this measure close to each other. Well, let's say this is one of those about 100, I think it's 131 or something, I don't know. Oh no, it's 126 point something. Let's say 126-ish. We're going to see that ish isn't really going to make much of a difference. So here's one angle of 126. Let's throw another one on there, 126-ish. What's this remaining angle? Well, it's 360 minus 252, which is what, 108. It's not exactly 108. So let's say it's approximately that, which is 108. So right here, we can't fit a third 7-gon in there. So we throw two up next to each other. We're not going to be able to fit a third one because this angle is too small. How about an 8-gon? Well, an 8-gon might be a little easier to illustrate because, well, they're easy to draw. But this is also, the interior angles measure is also a number. I'll tell you this equals 135 because it's what? 180 times 6/8, 180 times 3/4, 180 divided by 4 is 45. 45 times 3 is 135. So if we take regular octagons, now let's just throw one up against it like this. Well, let's work up here. Can we fit another octagon in here? 135 and 135. What's this angle up here? Well, it's 90. Why is it 90? Well, 135, 135, 270. 270 from 360 is 90. So we can't fill it in with octagons. And for any angle, for any n-gon larger than a 6-gon, the interior angle is going to be larger than 120, but less than 180. So this situation is always going to happen where you put two up next to each other, you create a small angle where you can't fit a third one in. And I'm not going to write that down as a statement. I'm just going to, I'll just put an end of proof, QED, quod erat demonstrandum, Latin for, it has been shown or something like that, by that discussion for larger than 6-gons. But for any larger than 6-gon, the interior angle is larger than 120, but less than 180, so you're going to create a small wedge where you can't fill it in. So we just showed that the only regular tilings which exist are tilings with triangles, squares, and hexagons. And we went through a proof with a good amount of detail. A very short abbreviation for the proof, which some of you may have observed probably when we were talking about hexagons, or maybe pentagons, is that we can make a tiling if the interior angle is divisible by 360. So in the equilateral triangle, the interior angle was 60. That's divisible by 360. For a square, 90 is divisible by 360. For a pentagon, 108 is not. For a hexagon, 120 is. And for anything larger than 6, the interior angles between 120 and 180, and none of those numbers are divisible evenly by 360. But I like the proof with those details. So the next question, we tiled with regular polygons. Polygons where all the sides were the same and all the angles were the same. What about tilings with irregular polygons? So polygons where the sides may not be the same length or the angles may not be the same. Well, first, let's talk about rectangles. No, let's not talk about rectangles. Let's talk about parallelograms, and then talk about rectangles. So can we tile, and again, we're only going to tile with one size shape. We're going to try to fill in all of two-dimensional space with the same parallelogram. Well, can we do this? Well, let's divide our two-dimensional space up into parallel lines again for this. Or into parallel strips, I should say. So it goes off in this direction, it goes off in that direction, and so on. Maybe I didn't need that last line. Well, can we fill this in with parallelograms? Yes. By just putting a parallelogram up here like this. Well, there's a parallelogram. Well, remember what happens in a parallelogram. The two top angles add to 180. So we can put, maybe I'll label the angles in it, at least the top angles. A, B, C, D. Notice A plus B equals 180. C plus D equals 180. And because of that, if we have angle B up here, we can fit a parallelogram right next to it. Angle A, angle B, angle C, angle D, and so on. And you can keep filling it in like that. So on the bottom, we have a straight line C plus D. On the top, we have a straight line B plus A, and so on. And now down here, well, all you have to do is extend that down. C plus B, now we're looking here. C plus B is 180. D plus A, 180, because of the other side of the parallelogram argument, and so on. So we can fill in two-dimensional space with parallelograms. Well, that's wonderful. What about rectangles? Well, rectangles are just a special case of parallelograms where all the angles are right angles. So with rectangles, it would look pretty much the same, except they'd be straight lines instead of slanted lines. I pretend those rectangles are all the same size. So they'd be straight lines instead of the slanted lines for a rectangle, because a rectangle is just a special case of a parallelogram where all the angles are right. What about triangles? Well, the most amorphous, let's say, a triangle can be is a scalene triangle. Let's draw a scalene triangle. So that looks kind of isosceles. Do I have a good scalene? Not really. Yeah, okay, that looks pretty scalene. So this is scalene. S-C-A-L-E-N-E. Can we fill in two-dimensional space with scalene triangles? So maybe I'll say yes for parallelograms. There is a tiling. Yes for rectangles. There was a tiling. Is there a tiling for triangles? In particular, is there a tiling for scalene triangles? Well, there was a reason I did the parallelograms first. Let's, I don't know, I guess I'll label the triangles, or the angles. But remember, if you take two of these triangles, I should label the sides actually, not the angles. Sorry if you wrote the angles in your notes. Let's label the sides. A, and I'll call that one C, A, C, B. So let's label these sides A, C, B. Well, if you let C act as kind of a a flipping axis and then rotate the triangle a little, you can create two triangles. So we have ACB, we have ABC, and those two triangles together make a parallelogram. So the observation, we can create a parallelogram using two copies of a triangle. And once you have two copies of the triangle, or once you have a parallelogram formed by two copies of the triangle, you can use these to fill in two-dimensional space, just as we did here. Now with triangles, what would that look like? Well, it would look just like that, except there'd be diagonal lines written. So I'll draw that like this. So here we have our A, C, B triangle. Well, we formed a parallelogram like that. A, B up there, C over there. And then you can keep going on. So right here we have a parallelogram. Well, and then we're going to just keep making the same parallelogram, and we'll divide the parallelogram in half like that to make our original scalene triangle, and so on. And down here it would just be the same type of thing but flipped around. So we would want B there, so we have A and C like that. So it's really and in the next row you'll notice that it kind of goes backwards because we want the edges to be preserved, but it's still going to be filled in with parallelograms. Where am I? So right here in this first piece we have this parallelogram. So we have this parallelogram up here, and then down here we have the same type of parallelogram written a little backwards, but the edges are still going to match up, and so on. So I'll just make a remark. We did it for a scalene triangle. For an isosceles triangle, the argument is the same. Make a parallelogram and fill it in with parallelograms. So I'll just say, as a remark, any triangle can tile the plane, and as a parenthetical, by using two triangles to make a parallelogram. Parallelogram is a really big word, so I usually just draw a little parallelogram. And then tiling it with parallelograms. So any triangle can work. So now we showed for parallelograms, we showed it for triangles. What about general quadrilaterals? So quadrilaterals, well, maybe I should say trapezoids first. Because trapezoids are cool. I like trapezoids. I actually didn't write this in my notes. But we can fill it in with trapezoids. How can we fill it in with trapezoids? That's not how you spell trapezoid. There. Trapezoids. Let's draw one that looks like this. Well, you can fill it in with trapezoids similar to the way you fill it in for parallelograms. Go in each direction infinitely far, fill it in with a trapezoid like that, and then you fill it in with that next trapezoid by like flipping it around, and so on. And then you want the edges to match up. So really, it make actually interesting. It's a good thing I decided to mention trapezoids, because these trapezoids, when you put two together, form a hexagon. So you could do it by filling it in with strips, or you could do it, these are what, regular trapezoids? Or you could do it by filling it in, creating a hexagon and then filling it with hexagons. General trapezoids, you won't be able to form regular hexagons. General trapezoids, you'd have to fill it in on the strips because trapezoids have one pair of parallel lines. What about general quadrilaterals? Well, what about general quadrilaterals? Well, I happen to have one right here, which I made by folding paper. I did this because I'm not good at drawing things. So, general quadrilaterals, I'm going to use this to trace out my quadrilateral. So right here we have a general quadrilateral. The first observation we make, observe or recall, from the first remark over here that I drew or that I wrote after talking about squares. The angles inside a quadrilateral add to 360 degrees. So A plus B plus C plus D, those are the four angles, add to 360 degrees. Well, that observation and a small amount of cleverness are all we need to use that quadrilateral to fill in the plane. Now, what do I mean by that? Well, let's draw one of them. So we'll start with this quadrilateral, and we'll label the angles A, B, C, D. Well, this side over here is CD. Our goal, well, maybe I shouldn't draw a circle. Our goal here is going to be, at a given vertex, to fill it in with angles A, B, C, and D, which we know add to 360. So let's do that. Let's work in this direction. So right here we have side CD. So I'm going to flip it around like this and put angle D up here. So now we have what? We have D, C, A, B. Okay? Great. Now we need angles. So, well, this side here is DA, so let's put angle A. I'm focusing on this vertex. So let's put angle A up there. We need that side to still be AD. So we'll mark the vertices, label as such. So that was angle A, B, C, D. And right now, we have A, D, and C, so all you have to do is fit angle B in there. And we can do that like this. And all I need to label is vertex D up there. So that's angle D, that's angle B. This up here is angle A, and that's angle C. And you can keep going using any of the vertices. Right here, we have C and D, so we would need to fill it in with A and B, and we'd also need to preserve this side. But you can do that with any vertex and fill in the entire plane with quadrilaterals. Now, what about, let's say, what about, so you might think that that covered all quadrilaterals. It technically did by an observation, by that ABCD observation. But what about quadrilaterals that look like this? So let's say we had a quadrilateral that looked like this. So it's, instead of being like bulged out at each of the angles, it goes in at one of the angles and creates an angle above 180. This is called a non-convex quadrilateral. Well, it's non-convex. The true definition of non-convex is that if you take, well, This is a non-convex. This is a convex quadrilateral. For a convex quadrilateral, any line connecting any vertices stays entirely in the quadrilateral. So here, if you connect A to C, that's in the quadrilateral, B to C, that's in the quadrilateral, and so on. Over here, if you connect A to D, that line is not going to be inside the quadrilateral. So that's what we call non-convex. I think it's easier to see with just a non-convex quadrilateral, what has an angle above 180. But can we use those to tile the plane? I'm not going to show you how, but I will say the answer is yes by this same process. Setting up the angles and the edges so that at each vertex you get 360 degrees. So we just showed that for any quadrilateral we can create a tiling. What about 5-gons? What about 6-gons? What about 7-gons, 8-gons, and so on? Well, I'm going to go to the textbook for that, and I'm just going to read a couple pieces of the textbook. Well, actually, maybe I'll show something too. Right here, I hope this shows. On page 834, it shows you just like, well, it shows a convex quadrilateral, how you can use that to tile the plane. It also shows over here how you can use a non-convex quadrilateral to tile the plane. So you might want to look at that. But also on this page it talks about 5-gons. We could hope that such success would extend to irregular polygons of any number of sides, but it doesn't. Which convex hexagons can tile the plane was determined by Karl Reinhardt in 1918. He showed that for a hexagon to tile, it must belong to one of 3 classes, which are shown on page 835. So the only hexagons that can tile the plane look like one of the 3 classes on page 835. Excuse me, 835. You can look in the textbook too, in case that doesn't show up on camera. So that shows for hexagons. What about pentagons? Reinhardt also explored tilings by convex pentagons and found 5 classes of pentagons that tile. Now, he thought that that was all of them. He said that it's all of them, but then he didn't prove that it was all of them. He said the proof was long, and usually when people say the proof is long, it means I suspect it's true, but don't want to go through the details. But in, what year? 1968. Some other person, R.B. Kirshner, a physicist, found 3 more classes of pentagons that tiled. And he said that was all of them. And he said, I don't have a proof, but it would require a rather large book. Possible. Reinhardt found 5 classes of pentagons. Kirshner found 3 more classes of pentagons by 1968. In 1975, an amateur mathematician found a 9th type. Marjorie Rice, a housewife with no formal education in mathematics beyond high school general mathematics, found a 9th type. She also found 4 more beyond that. So, and on page 836, there's a page of a Spotlight 20.2 on her, and it talks about her. Well, that's definitely worth reading. I never heard of her until reading through this textbook. I thought that was an enjoyable read, that page, 836. So Reinhardt found 5, Kirshner found 3 more, Marjorie Rice found 5 more. The way she found 5 more was actually not dissimilar to what I was doing with this. She said that, well, the book says that she was just playing around with shapes until she found some. Now, sometimes math is discovered like that. You just play around with things until you see something. So now we have 13 classes of pentagons which tile. A 14th type was found by a graduate student in 1985. A 15th type was found in 2015 by researchers at University of Washington, Bothell. Never heard of it. And they used computers to find that 15th. The first 14 were not done using computers. And right now there actually is an open question in mathematics. Are there more than 15 or are there exactly 15? So right now there are 15 known. If you want to find yourself in the mathematics history books, you can either prove that there aren't any more, or you can find others, and then possibly prove there aren't any more. So we showed tilings for 3 gons. We showed tilings for 4 gons. There are 15, possibly more, tiling or classes of 5 gons which tile. There are 3 classes of convex hexagons which tile. And 4 polygons of larger size, larger number of sides than 6, there are no convex 7 or 8 or anything larger gons which tile the plane. So definitely, I mean, this construction definitely takes a little bit of practice. I think that's worth practicing. That there is going to be one of those on a worksheet. Find a quadrilateral and do a tiling just like that. But these are definitely worth looking at. One other type of tiling, I'm not going to ask anything on this, so, well, I'm not going to ask anything on it. But pages 8, you should definitely just go through these pages. 837 through 843 talk about other tilings by Moritz Escher. Moritz Escher was a mathematician. There's a couple pages on, or a half a page talking about him on 837 to 838. That's worth reading. But a couple other tilings that you can go through. Basically, you take a parallelogram, for example, and you chop off a hunk over here and you move it over here, and you keep doing that a few times. You can use that to create some interesting looking tilings. And just as an example, page 840, there is this one. Hopefully that shows up. So they start with this parallelogram, chop off some hunks, move them around, and you're left with a shape like that, and you can use that to fill in the plane. So I definitely think it's worth flipping through and reading some of the things on pages 834 through 843 at some of those tilings.